முக்கியமா. Very good afternoon to all. So this is first day of GATE class, and few more students to need to join. So we also record this entire meeting for our upcoming and future preference also. Okay, so I will share the recorded video link for your preparation. Okay, during the session, all of you can stay online only. So during the session, if you have any queries, any doubt, means kindly ask to our resource person. Okay, so our resource person is engineer Naveen Arasu sir. So he is doing in research and completed ME and industry experience and educational experience also. So now I invite our resource person, Naveen Arsa sir. Take the session, sir.
Sir, thank you, sir.
Yeah, okay, sir. சார் ஸ்டூடெண்ட்ஸ் வந்து கொஞ்சம் நார்த் இந்தியன்ஸும் இருக்காங்க, தமிழ் ஸ்டூடெண்ட்ஸும் இருக்காங்க. ஸோ நீங்கள் போத் வே
Okay.
நீங்கள் மேனேஜ் பண்ணிக்கோங்க சார்.
Okay, sir.
ஓகே சார், ஓகே. தேங்க்யூ சார்.
Thank you, sir. Okay, good afternoon, students.
Good afternoon, sir.
Myself, Naveen, working as an assistant professor in CMS College of Engineering, as well as I'm doing my doctorate in Karpam University also. And I'll be taking care of the mechanics of solid subject for you in this GATE coaching class. Okay, guys, whether my screen is visible to you?
Yes, sir. Visible, sir.
Okay, pa.
Yes, sir. Possible, sir.
Okay, pa. Thank you. And at the starting itself, I have to clearly say that in just 2 hours class, we cannot complete the entire mechanics of solid subject. So I'll be going little bit faster. And if I'm going faster and you are not able to understand, na, you can just stop me and you can ask your doubts. Okay, and the entire all the problems or the derivations, the entire things cannot be completed. Okay, in just 2 hours of time. So I'll be speaking only about the important things, and as far as GATE exam, how the questions will be asked and what are the basic things. That's what I will be going to touch in this sessions. Okay. Okay, this is what the syllabus which is given by the GATE committee for 2022 examinations. Okay, the bending moment and shear force in statically determinate structure, determinate beams. Okay, statically determinate beams. Now, examples: cantilever beams, simply supported beams, etc. For that alone is more than enough for you. You don't have to go for statically indeterminate beams like propped cantilever beams, then fixed beams, etc. Okay. Then simple stresses and strain relationship. What is the relationship between the stress and strain? I think you all know about the UTM, right? You have everyone have done a test about the mild steel bar. That for that you'll have drawn a graph now. That's what you'll be studying on it. Next, the theory of failures, then simple bending theories, flexural and shear stresses, uniform torsions, buckling of columns, combined and direct bending stress. These are the topics which we are going to see in this session. Types of beam. Normally we have six types of beam. One will be the cantilever beam, then a simply supported beam, overhanging beam, continuous beam, fixed beam, and cantilever simply supported or propped cantilever. Yeah, the sixth type alone, it has two names in it, and these are the pictures of it. Okay, I think you don't. I don't want to give a brief explanation about each and every type of beam, right? Guys, this alone is more than enough for you, or you want me to explain detailedly about each and every type of beam? Anyone can unmute yourself and speak.
Please explain, sir.
Okay. Okay, in the cantilever beam, அப்படின்னா, one end of the beam will be fixed and other end of the beam is free அப்படின்னா, then it is called as a cantilever beam. In the simply supported beam அப்படின்னு பார்த்தோம்னா, the word itself, they have clearly mentioned that it is just simply supported. ஓகேங்களா, it will be just simply supported at both ends of the beam. ஓகேங்களா. Then overhanging beam. In the overhanging beam, we have two types. One will be single overhanging and second one will be the double overhanging beam. In this picture, I have pasted a double overhanging beam. The overhanging will be on two sides. Abdina, then it is called as a double overhanging. If it is a single abdina, one end of the beam will be not overhanging. You will be having a support like simply supported, or it may be a roller support or fixed support, and one end of the beam alone will be overhanged. Okay. Next one will be the continuous beam. The continuous beam, you have numerous types of continuous beam. It may be a fixed continuous beam or a simply supported continuous beam or a roller supported continuous beam or a combination of any two. Okay. Uh, any beam, when it has more than two supports, then it is called as a continuous beam. Okay. Then fixed beam. When both ends of the beam is fixed, then it is called as a fixed beam. And the last one will be the propped cantilever beam or cantilever simply supported beam. Why this type of simply supported end is provided அப்படின்னு பார்த்தீங்கன்னா, when the span of the cantilever beam is more, what happens? The deflection will be happening at the free end. In order to reduce the deflection at the free end, it will be just supported with a small simply supported structure. Okay, to reduce the deflection at the free end. Okay. These are the types of beams. Next, what are the common types of load which occurs on a beam அப்படின்னு பார்த்தீங்கன்னா, first one will be a concentrated or point load. At a particular point alone, the load will be happening. Either it may be at the middle of the beam or at the end of the beam or any portion. At only at particular point, if the load is applied, then it is called as a concentrated or point load. Second one will be the uniformly distributed load. The load will be distributed throughout the beam structure. Example பார்த்தீங்கன்னா dead load, because dead load will be uniform throughout the beam structure, right? So that is one of an example of UDL. Next, uniformly varying load. Uniformly varying load அப்படின்னு பார்த்தீங்கன்னா, at one end of the beam பார்த்தீங்கன்னா, the load will be zero, whereas at the other end it will be maximum and it will be varying in uniform manner. Okay, like this. Uniformly, if it is varying அப்படின்னா, then it is called as a uniformly varying load. Next one will be the concentrated moment. The moment will be at the fixed end. In case of a fixed beam அப்படின்னு பார்த்தீங்கன்னா, you will be having a moment. ஓகேங்களா. So that concentrated moment at that point, even if it is of what to say, continuous beam, the intermediate supports, you will be having a moment. Okay, for example, in this picture you could see four supports, right? This intermediate two supports, even at there it is a simply supported beam or roller supported beam, you will be having a moment since it is in between two supports. Okay, that is called as concentrated moment. Next we are guys, do you have any doubt up to this?
No, sir.
Okay. Okay, next we are going to see about what is shear force and what is bending moment. First of all, what is shear force அப்படின்னு பார்த்தீங்கன்னா, it is just an algebraic sum of vertical forces acting from left to right or right to left of the cut section. Okay, simple இன்னும் இன்னும் simply if you want me to explain அப்படின்னு பார்த்தீங்கன்னா, uh, for shear force you will be adding the load in case of point load. In case of UDL அப்படின்னா you will be adding the load into distance. It is called shear force. In case of bending moment ன்னு பார்த்தீங்கன்னா, it is just the algebraic sum of moments of forces from left to right or right to left of the cut down section. And in simplified manner அப்படின்னு பார்த்தீங்கன்னா, the formula for calculating bending moment is load into distance in case of point load, and in case of UDL அப்படின்னா load into distance by 2. This is a formula to calculate the bending moment of the structure. Okay. And this is some common formulas for it and common pictures. If it is the first picture பார்த்தீங்கன்னா, it will be a cantilever beam and the load is acting at the B point, that is the free end of the cantilever beam. And there is a constant things. What are they அப்படின்னு பார்த்தீங்கன்னா, for a cantilever beam always the shear force will be positive. ஓகேங்களா, and always the bending moment will be negative. For a cantilever beam, don't forget it, for a cantilever beam the shear force will be always positive and the bending moment will be always negative. What is the reason அப்படின்னு பார்த்தீங்கன்னா, you will be having only the downward load, you don't have any reactions, so that only this is the concept. In case of a simply supported beam அப்படின்னு பார்த்தீங்கன்னா, okay, simply supported beam is not available. So in case of simply supported beam பார்த்தீங்கன்னா, you will be having reactions at the both the ends, right? At both the ends, since you have a reaction, the positive and negative shear force will be there. Even the bending moment in பார்த்தீங்கன்னா, there will be some positive and bending moment will be acting over it. And where the maximum bending moment will be there அப்படின்னு பார்த்தீங்கன்னா, where the shear force changes from positive to negative, at that particular point the bending moment will be maximum. ஓகேங்களா. Okay. And this is some diagrams of shear force and bending moment diagram based on the load conditions. For a simply supported beam, the first picture, if you look at it, a point load which is acting at the center of the beam. In that case, how the shear force diagram will be there அப்படின்னா, this is how the diagram will be there. ஓகேங்களா. And the bending moment will be in a triangular manner. Why there is some positive and negative shear force அப்படின்னு பார்த்தீங்கன்னா, you have reactions at both the ends of the beam, as well as you have a point load which is acting downwards and the reaction is acting in the upward direction. So at one particular point there will be some changing from positive to negative signs, right? At that particular point only the bending moment will be maximum. I have already said no. That's why the bending moment is maximum at the center. In case if it is a UDL na, this is how the diagram will be there. ஓகேங்களா. This one will, the right side of the diagram will பார்த்தீங்கன்னா கீழே இறங்கி இருக்கு இல்லையா, that is due to the reaction, and this inclined line for a load in reaction where the bending moment will be maximum சொல்லியிருக்கோம் at the mid span. So at the mid span the shear force will be always 0, and for a UDL load the moment will be in a parabolic shape, whereas in a point load அப்படின்னா the moment will be in a inclined line. ஓகேங்களா. Then third one will be the uniformly varying load. In case of uniformly varying load அப்படின்னா the shear force பார்த்தீங்கன்னா always it should be drawn in the parabolic form. ஓகேங்களா. The parabolic form it will be drawn. See, the left side and right side இருக்கிற lines will be for reactions, and the parabolic curve, that is based on the load which acting on the surface. And this is the bending moment diagram. It will be in a cube manner. why it is not in a parabolic, instead of it why it is cubical manner அப்படின்னா there will be uniformly varying load. See, at the left end the load is very minimum and at the right end the load is maximum. Since due to that only there is a cubical shape. Okay. Next comes the load. In case of moment, how the diagram will be there அப்படின்னா it will be constant rectangular shape. In case if it is a moment அப்படின்னா it will be in a linear manner. Moment எங்க இருக்கு? At the center. So at the center point the bending moment will be maximums. ஓகேங்களா? And the load if it is at the free end cantilever beam if it is in a free end அப்படின்னு பார்த்தீங்கன்னா then also the shear force will be at the rectangular shape and the moment will be in a triangular shape, that is linear. And the if it is a uniformly distributed load which is acting on a cantilever beam now the shear force will be in a triangular and the moment will be in a parabolic shape. Okay, this is a basic diagrams for shear force and bending moment. Okay guys, do you have any doubt up to this shear force and bending moment?
No, sir.
Okay. Next we will be seeing about the slope and deflections. Okay, slope and deflection it is also defined as a defined by Morse person. So Morse have defined two theories, Morse theorem 1 and Morse theorem 2. For Morse theorem 1 it includes the slope and Morse theorem 2 it includes the deflection of a beam. Okay. Here I have taken the 6 main types of beams. For that I have given some formulas. That is the maximum bending moment, slope and deflection formulas. It can be derived and or you can study the formula. For as far as GATE exam is concerned, you will be having a very limited time. So no other go, you have to study all the formulas in order to reduce the time for solving the problems in it. Okay. Okay, now let us see the formulas one by one in a detailed manner. In case of a cantilever beam, where only moment comes அப்படின்னா maximum bending moment will be the moment. What moment comes into a beam that will be the maximum bending moment. And for the slope, what is the formula அப்படின்னா theta equal to ml divided by ei, where m will be the moment and length L will be the length of the beam. E will be the Young's modulus of the material. I will be the moment of inertia. Both together EI is called as modulus of rigidity. Okay. In case of diffraction, del equal to ml square divided by EI, sorry, 2EI. Similarly for point load, what will be the maximum bending moment? It will be WL and the pi value, that is the slope, is WL square divided by 2EI, where W will be the load acting on the structure, L will be the length of the structure, and E will be Young's modulus and I will be the moment of inertia. Okay. Okay, you can just go through this formula for a minute. Okay. If you have any doubt regarding this shapes அப்படின்னா you can ask. No other go, you have to memorize it. If you are going with derivating and finding this formulas அப்படின்னா you could not complete all the questions in the gate. Okay. So you have to memorize it. Only you can see the diagrams. If you have any doubt in the diagram அப்படின்னா you can ask. First picture will be the cantilever beam with end moment, and the second one will be the cantilever beam with end point load. Third diagram pathina will be having a cantilever beam with the UDL load throughout the beam, and fourth diagram cantilever beam with uniformly varying load. Fifth picture simply supported beam at a point load at the midspan, and last diagram will be the simply supported beam with the UDL throughout its span. Okay. In Moore's theorem 1 and 2 ல பார்த்தீங்கன்னா even more simplified அப்படின்னா Moore's theorem 1 we have a formula, basic formula, that is A divided by EI, where A will be the area of bending moment diagram. In case if it is of Moore's theorem 2 for diffraction அப்படின்னா the general formula will be A x bar by EI. A will be the bending moment of that particular section and x bar will be the centroid about x axis. Okay, okay. Now we can go into the next one, that is the stress strain curve for mild steel. Normally where the stress and strain will be occurring அப்படின்னா not only in mild steel, in all the areas we will be having a stress strain relationship. Okay, due to the stress and strain creating in a material, it causes the crack, defects or failure of the section. So in the mild steel we will be checking over it. Okay, so first point, that is from O to A, it is called as a linear region. If you release the load, automatically the material will be regaining its original shape. That is called linear region. Okay, at the area of A and C, sorry, A to B அப்படின்னு பார்த்தீங்கன்னா it is called as a yield stress, where there will be a difference between coming back into original position or there will be some variations, that is called as a yield stage. And B to C அப்படின்னு பார்த்தீங்கன்னா it is called as a plastic stage. Okay, where plastic stage ஆயிடுச்சு, it does not regain its original shape. Okay, or permanent deformation happened. And from C to D, that will be the strain hardening or the ultimate stress at the D point, the maximum load that the mild steel can achieve. After that, the load will be keep on decreasing, and at a particular point the steel will be completely broken. Okay, that is called fracture limit. At the point D and E, the mild steel thickness will get reducing and reducing. Okay. That's all about the shear force bending moment diagrams, then a relationship between stress and strains. And we have some formulas also related to stress and strain. Okay, before going to the theory of failures, I'll say about the formulas also. What is the formula to calculate the stress? Anyone can unmute yourself and speak. What is the general formula to find the
Force by area,
stress?
sir.
Good, force by area or load by area. Okay, what is the formula to calculate the strain? For strain, you have two types. One will be the longitudinal and the second one will be the linear strain. For a longitudinal strain, what is the formula? Change in longitudinal dimension divided by original dimension. Okay. Similarly, for lenient பார்த்தீங்கன்னா change in breadth or change in thickness divided by original thickness or original breadth of the section. That is the formula to calculate. And normally the unit of stress is Newton per mm square, and for strain you don't have it units. Okay. Okay. Now we can see about the theories of failures. To predict the elastic failure under any conditions from the behavior of material in a simple test, the different theories for different materials and parameters that are considered. What are they? First one will be the maximum principal stress theory, then maximum shear stress theory, then maximum distortion energy theory, then maximum strain energy theory, and finally the strength of the materials, what we have to study, whether it may be a steel or concrete or RCC structure. These are the five major theories of failures. Due to this only the failures may occur. And we have some assumptions in the theory of bendings. What are they அப்படின்னு பார்த்தீங்கன்னா, normally the material of a beam is isotropic and homogeneous and follow Hooke's law. And here the stress induced is proportional to the strain, and the stress at any point does not exceed the elastic limit. And these assumptions I will share the PPT also. So if possible, after the class we'll see the assumptions. ஓகேங்களா? ஏன்னா assumptions மட்டுமே பார்த்துட்டு இருந்தா, நம்ம தியரி மட்டுமே பார்த்துட்டு இருந்தா, it will consume a lot of time. Okay. Okay, this is the bending equation. Normally, for any structure we'll be using. Okay, what is the bending equation? Pathina m divided by m by I equal to stress by y equal to E by R. This stress symbol can also be indicated as F, and there is a small way to remember this equation. What is that? அப்படின்னு பார்த்தீங்கன்னா, may I follow you, Elizabeth Rani. This is a small way to easily remember this bending equation. M for may, I for may I, stressக்கு வந்து follow, Y வந்து you, may I follow you, Elizabeth Rani. By using this small thing, we can easily memorize this bending equation, where M stands for the moment of resistance and I will be the moment of inertia of the section about the neutral axis. Then E will be the modulus of elasticity of a material. R will be the radius of curvature of a neutral axis. Then sigma will be the bending stress at a point, and y will be the distance of a point from neutral axis. In case if you have to find any one thing, that is for example stress எடுத்துட்டீங்கன்னா, sigma equal to m by I into y, any one we can calculate. For example, E by R, E or R is unknown அப்படின்னா, we can use this first equation. If m or I is not given அப்படின்னா, then sigma is equal to E into y divided by R. Anything we can substitute here. Okay. And the variation of bending stress along the cross section is linear. How the diagram will be there அப்படின்னா, this is the diagram of it. ஓகேங்களா? At the top portion it will be in positive, and at the below the neutral axis it will be in the negative signation, negative variation. This is the variation and bending stress. This is how it will be looking like. The neutral axis, when it's called as a neutral axis அப்படின்னு பார்த்தீங்கன்னா, guys, am I audible to you?
Yes, sir.
Okay. When the or what to say, how a neutral axis is defined அப்படின்னு பார்த்தீங்கன்னா, where you don't have any compressive load or tensile load at that particular point is called as a neutral axis. Okay. Above the neutral axis, it is called as the positive, and the below the neutral axis it is will be the negative neutral axis. Okay, sorry, negative moment. And the neutral axis is the axis which the bending stress is zero. The neutral axis is always passes through the centroid of the section of beam. For a cantilever beam, how it will be அப்படின்னு பார்த்தீங்கன்னா, the top portion is called as a tensile zone and the bottom is called as the compressive zone. And the intermediate, the line between that is called as the neutral axis. In case if it is a simply supported beam அப்படின்னா, it will be in the reverse manner. The top portion will be the compression zone and the bottom portion will be the tensile zone. That is the main reason we are providing our reinforcement at the bottom. That is the main reinforcement at the bottom of the beam. Have you ever noticed that? I think we have everyone have gone to internships, right? Have you ever noticed most of the main reinforcements will be provided at the bottom of the beam, right? Even in DRC you have studied, no?
Sir, to resist the compressive and compressive.
Yeah, good. To resist the compressive as well as the to take care of the tensile load. Okay, so normally the main reinforcements will be provided at the bottom portion, and most of the beams what you will be deciding will be simply supported or continuous beams. Only the cantilever beams where and all you will be providing patina at the porticos or simple இன்னும் சொல்லணும்னா like sunshades, it will be a cantilever projections. Only at that particular point, the main reinforcement will be at the top. In all other areas, the main reinforcements will be only at the bottom portion of the beams. Okay. And for a sectional modulus, the bending stress equation will be sigma equal to my by I or mz. Then section modulus z equal to I by y. Instead of I by y, it is also called as section modulus. Normally, the unit of what to say moment of inertia will be always in power 4, whereas in section modulus it will be in the unit cube. The bending stress occurs at the extreme distance from neutral axis, that is m is equal to sigma z. For a given material of a beam, m will be directly proportional to z, that is moment will be directly proportional to sectional modulus. Next, for a triangle section, how the neutral axis will be there? Normally, the neutral axis will be at the center portion of now. What are the formulas to calculate the moment of inertia, then y maximum and section modulus? That what we are going to see in this slide. The moment of inertia for a section about neutral axis I is equal to BD cube by 12, where B will be the breadth of the section and D will be the depth of the section. You can see we will be using only the small d, so that we have to take down the effective breadth and effective depth of the section. And y max will be at a distance of d by 2, and section modulus z equal to I by y or bd cube by 12 divided by d by 2, or simply it is called as bd squared by 6. Similarly, for a hollow rectangular section, since it is hollow, the hollow portion we have to subtract it. So the moment of inertia I equal to 1 by 12 into BD cube, that is capital BD cube minus small bd cube. Capital B will be the breadth of the outer portion, and d will be the depth of the outer portion, and small b will be the breadth of the inner portion, and small d will be the depth of the inner portion of the section. And y maximum will be the capital D by 2. Small d by 2, you should not take it. And for the section modulus, capital BD cube divided by small bd cube divided by 6d. This is the formula to calculate. Guys, do you require 1 or 2 minutes to go through each and every formula, or let me take the class continuously?
So take the class continuously and post the formulas in the group, sir.
Okay, pa.
Share this PPT in the WhatsApp group, sir.
Okay, pa. I'll share the PPT to Parthasarathi sir. Okay, you can get it from him.
Okay, sir. Okay, sir.
Next, for a circular section, the moment of inertia, what is the formula? I equal to pi d squared by 64. This is the formula. For y maximum, it will be the same d by 2. And the section formula, sorry, section modulus z formula, z equal to pi d cube by 32 in case of diameter. In case instead of diameter they have given radius அப்படின்னா z equal to pi r cube divided by 4. These are the formulas to calculate. Next, if it is a hollow circular section, the moment of inertia I equal to pi by 64 into capital D power 4 divided by small d power 4. And y maximum will be the d by 2, that is capital D by 2. And section modulus z equal to pi into d power 4, that is capital D power 4 minus small d power 4, the whole divided by 32d. That's all about the formulas related to section modulus and moment of inertia. Now we are going to see about the beam of heterogeneous material. When a beam is called as a heterogeneous material, when the beam is when you are going to design a flitched beam, then it is called as a heterogeneous material. A fixed beam is nothing but a beam reinforced symmetrically about the neutral axis. Then it is called as a fixed beam. Normally, the fixed beams are used to withstand the load greater than the normally allowable load. Mostly in cases of high-rise buildings or in case any moving load is happening on that particular structure, in those type of thing areas will be going this type of fletched beams. The reinforcing material should have higher modulus of elasticity than the material of the beam. The total resisting moment at any section is the sum of resisting moment caused by the individual material making up the section. M is equal to M1 plus M2, where M1 will be the resisting moment of the beam material and M2 will be the resisting moment of the reinforcing material. Normally M1 will be taking for concrete and M2 will be taking care of the steel. And each material bent independently about its own neutral axis to the same radius of curvature. So same bending அப்படினாவே the same bending equation we have to take. That is m divided by I equal to sigma divided by y equal to E divided by R. 1 and 2 it will be based on the materials. The dimension of this section controls the stress ratio at the outer fibers of each material and therefore controls the value of the resisting moment. If the two materials joined firmly, normally the concrete RCC the concrete and the steel will be joined very firmly. In that case, what will be the formulas to calculate? E1 equal to E2, that is sigma 1 divided by capital E1 equal to sigma 2 divided by capital E2. In case any stresses are not given, that is stress of steel or stress of concrete, any one is not given அப்படின்னா we can calculate by using this formulas. Here E2 divided by E1 it is called as M, that is modular ratio. The moment of resistance of fletched beam is the same as that of wooden beam of width B plus 2m T and the depth D. And this is the some diagrams based on it. Either the reinforcement may be in the edges or at the intermediate or at one particular edge alone. Everything will be varying it in case of fletched beams. Next topic will be the beam of uniform strength. When a beam will be a uniform strength அப்படின்னு பார்த்தீங்கன்னா when you provide proper reinforcements, that is at the bottom you will be providing the tensile reinforcement and at the top also you will be having some hanger bars and concretes. Both act together and have a uniform strength throughout the beam section. This type of beams. Here, in case of cantilever carrying concentrated load at free end, அப்படின்னா what will be the section modulus and maximum bending stresses? அப்படின்னு பார்த்தீங்கன்னா Z equal to BD squared by 6 and the maximum bending stress will be 6Wx divided by BD squared, where X will be the bending moment, so distance between the edge and the bending moment. See, this is how the diagrammatic representation of it. This is a cantilever beam and the load W is acting at the edge. And X will be the distance between the bending moment or the neutral axis from that point to this load, that is called as X distance. When D is constant, that is the depth of the beam is constant அப்படின்னா width at section XS equal to BX equal to 6WX divided by sigma D squared, where BX is directly proportional to X. At X is equal to 1, in case X or distance if is 1 meter அப்படின்னா B is equal to 6WL divided by sigma D squared. In case breadth of the beam is constant அப்படின்னா the depth of the section xx, that is about xx direction, equal to பார்த்தீங்கன்னா root of 6wx divided by b sigma. Here dx is directly proportional to root x. At x is equal to 1, d equal to root of 6wi divided by b sigma. This is how the formulas. Based on the load how the bending moment profile will be looking like. Next, for a cantilever beam with a carrying of UDL. In the last class, we have seen about for point load, and now we are going to see about the uniformly distributed load. For that area, if you are going to cut down this section, that is at xx cut பண்றோம். At that particular point, what will be the bending moment அப்படின்னு பார்த்தீங்கன்னா m equal to wx squared divided by 2. W will be the load acting on the structure, and x ங்கிறது பார்த்தீங்கன்னா இந்த கட் டவுன் பண்ண x ல இருந்து edge of the beam உள்ள distance, that is called x. And the section modulus formula will be the same for a rectangular section, that is bd squared by 6. And maximum bending stress sigma equal to m by z equal to 3wx squared divided by bd squared. Here also we have the same thing. When d is constant and b is constant, for that what is the formulas? And in case if x is equal to 1 அப்படினா what will be that value? Okay. Next one பார்த்தீங்கன்னா for a simply supported beam with point load at mid span. So the bending moment about this section பார்த்தீங்கன்னா mx equal to wx by 2. Here also we will be cutting down the section at a xx direction in any portion of a beam, and that is called x. That distance is called as the x. Section modulus formula, we have the same formula, and bending stress formula பார்த்தீங்கன்னா equal to 3wx divided by bd squared. And for that also the formulas will get changed. That is when d is constant அப்படின்னா what is the width of midsection about xx direction, bx is equal to 3wx divided by sigma d squared. At x is equal to L by 2, because the load is acting at the intermediate. In cantilever பார்த்தப்ப என்ன ஆச்சு, the load is acting at the free end, whereas here the load is acting at the midspan. So normally x will be taking it as L by 2. So what is the formula to calculate the width of the section அப்படின்னு பார்த்தீங்கன்னா b is equal to 3wl divided by 2 sigma d squared. When d is constant அப்படின்னா the depth of the section xx is பார்த்தீங்கன்னா dx equal to root of 3wx divided by b sigma, where dx is directly proportional to root of x. Here also at x is equal to L by 2, d is equal to root of 3wl divided by 2b sigma. Next, in case of simply supported with the UDL load, what will be the formula get changed? It is mentioned here. Okay guys, do you have any doubt up to this? Because after this slide we are going to see some problems related to what we have seen in this class. Guys, do you have any doubt up to this? Guys, do you have any doubt up to this?
No, sir.
Okay. Okay, guys, now we can see some of the 1 and 2 mark questions which is asked in the previous GATE exams. Okay. Only thing, if you are not, what to say, Uh, if you are not comfortable with the formulas அப்படின்னா the problems வந்து it will be more difficult to you. So, now the first question, the maximum bending stress induced in a steel wire of modulus of elasticity 200 kilonewton per meter square, sorry kilonewton per mm square, and the diameter is 1 mm. When wound on a drum of diameter 1 meter is approximately equal to, what will be the maximum load? What is the bending equation formula? Bending equation formula will be m by I equal to E by Y, sorry, F by Y equal to E by R. By using that formula, we can calculate the bending equation. Sigma equal to E by R into Y. Here, E, that is the Young's modulus, is known. Then Y is also known and R is also known. By using this, if you solve, you will be getting 200 Newton per mm square. That is the option C. Okay, this is just one more question. Okay, gate exam, if you solve this, you will be getting only 1 mark. Guys, do you have any doubt in this problem? Yeah, tell me, Pa.
No, sir, diameter it's that converted into radius. That's what 0.5.
Yeah, okay. Okay. And the second question, the basic assumptions of plane section normal to the neutral axis before bending, remaining plane and normal to the neutral axis after bending leads to which one? Uh, that's the reason I have added the assumptions, but due to the time shortage, I have skipped one. So in this one, the third one, that is linearly varying strain over the cross section. Okay, this is the answer. Due to the time shortage, I have skipped the assumptions. Even from that, the questions will be asked. Third question, the dimensions for the frictional rigidity of a beam element in mass m, length L and time t is given by. What is the dimensions of a flexural rigidity of a beam? Normally, flexural rigidity of the beam is called as EI. Already I have mentioned no. A divided by EI, or where EI is commonly known as flexural rigidity. So for E, what is the unit? Young's modulus, it will be kilonewton kilonewton per meter square or Newton per mm square. Okay, and for I, it will be mm power 4 or meter power 4. If you solve that, you will be getting m l cube t minus 2. T minus 2 is nothing but m l cube divided by t squared. Okay, next problem. A simply supported beam of uniform rectangular cross section of width b and depth h is subjected to linear temperature gradient 0 degree at the top and t degree at the bottom shown in the figure. The coefficient of linear expansion of the beam material is alpha. Then the resulting vertical deflection at the midspan of the beam is. What will be the answer, Pa? Anyone try to solve and say, even if it is wrong, that is not an issue.
Third one.
Then I am not able to clearly identify you. Which one option? Option A, B, C, or D?
Sir, I guess C.
C. That is alpha TH square divided by 8L downwards. Okay. But it is option D. How it comes அப்படின்னா, the average change in temperature is T by 2, right? Since we have two portions, top and bottom. Top என்ன கொடுத்திருக்கோம், we have 0 and at the bottom it is T degree. So the average in பார்த்தீங்கன்னா 0 plus T degree divided by 2 will be getting T by 2. Okay. Then the compression of the top flange fiber. Compression, what will be the L alpha T by 2? That will be the compression of the top fiber. That is length into stress into temperature variations. Next, elongation in the bottom fiber. L alpha T by 2. See, at the elongation, at the bottom portion, elongation will be there, and at the top portion, there will be contraction. Okay. The temperature strain E naught equal to L alpha T divided by 2L. We can simplify it as alpha T divided by 2. And reflection at the midpoint is downwards. By using the bending equation, M by I equal to sigma by Y equal to E by R. By using this, we can solve and find out the answer. That is alpha T L square divided by 8H, and it will be acting in the downward direction. How it is acting in the downward direction? The maximum temperature is at the bottom portion, so it is acting in the downward directions. Okay. Next question. A homogeneous simply supported prismatic beam of width B, depth D, and span L is subjected to a concentrated load of magnitude P. The load can be placed anywhere along the span of the beam. The maximum flexural stress developed in a beam is. What will be the maximum flexural stress? You don't see the answer. You can just try to solve on your own and say. Okay, how this answer is came அப்படின்னா, the maximum bending moment will be developed at midspan when concentrated load P is placed at the midspan. Okay, so that what will be the formula to calculate the maximum bending moment? The shear force and bending moment formula I have mentioned. PL by 4 or WL by 4 I have mentioned. Okay, and the moment of inertia formula for rectangular section is BD cube divided by 12. And Y maximum will be D by 2. So by using the maximum flexural stress, sigma max is equal to M by I E into Y, the same bending equation. E by R alone we have not taken, so M by I equal to F by Y, that formula we have taken. And substitute all the values. Instead of M, it will be PL by 4 and I bala BD cube by 12, and for Y it is D by 2. If you substitute these values, you will be getting 3PL divided by 2BD squared. Next, a beam with a cross section given below is subjected to a positive bending moment, causing compression at top of 16 kilonewton meter acting around the horizontal axis. the tensile force acting on the hatched area of the cross section is. Up to the previous sum, பார்த்தீங்கன்னா they have asked us to calculate the friction for the whole section or stress the for whole section. Whereas here they have asked us to calculate only for the hatched section. So for this hatched section alone we have to calculate. ஓகேங்களா? So for that, what should be done அப்படின்னா, first step we have to calculate the moment of inertia of that particular section. Sorry, moment of inertia of the bigger section, that is BD cube by 12. After that, we have to calculate the Y max, that is D by 2. That is 150 divided by 2 will be 75 mm. And the sigma max is equal to M divided by I into Y. That same formula, if you substitute, you will be getting an answer. That sigma max should be divided by the Y and multiplied by the thickness of the hatched area. If you substitute, you will be getting the bending tensile stress of that hatched portion. Stress max, that is sigma max already we have calculated, divided by Y max into depth of the hatched area. Okay, this formula alone is different. If you substitute in it, you will be getting the bending stress. Next, tensile force on the hatched area. T is equal to cross-sectional area into average stress. Cross-sectional area of the hatched section. So what is the cross-sectional area? It is 50 into 25. So 50 into 25 into average stress. So bending stress divided by 2 will give you the average stress. If you substitute, you will be getting 8.9 kilonewton. This is how we have to solve it. Okay. Guys, do you have any doubt up to this? Because the theory portion or the formula, it will be a lot easier. While solving problem, it will be little bit difficult, and it will be there some complications also will be there. Guys, anyone can unmute yourself and speak. Whether we can go with the problem solvings or only the theory and formulas.
Sir, let's do the problem, sir.
Okay, good. The following statements are related to bending of beam. First one, the slope of the bending moment diagram is equal to shear force. That is not correct. Then the slope of the shear force diagram is equal to the load intensity. That is also false. Then the slope of the curvature is equal to the flexural rotation அப்படின்னா yes. How it is equal அப்படிங்கிறது தான் பார்க்க போகிறோம். The slope of deflected curve is equal to the slope, sorry, this question is completely wrong, I think so. So we'll skip this and go into the next one. The plane section remains plane. Assumptions in bending theory implies என்னன்னு பார்த்தீங்கன்னா the strain profile is linear, stress profile is linear, both strain and stress profiles are linear, shear deformations are neglected. Which one அப்படின்னு பார்த்தீங்கன்னா strain profile is linear. How அப்படின்னா we have from that assumption the plane section remains plane. Assumption in bending theory implies strain profile is linear. From that bending theory it indicates. See, at the neutral axis the stresses will be zero, and above the neutral axis we have a positive bending moment, and below the neutral axis you will be having a negative bending moment. That's what it says. The first moment of area about the axis of bending for a beam cross section is moment of inertia or section modulus or shape factor or polar moment of inertia. We'll be having the first moment of area is based on mathematical constant moment in metric shapes. The first moment of area is equal to the summation of the product of area of its distance. That is sigma t into AIXI, where A will be the area of the section and X will be the centroidal distance. It is a measure of the distribution of the area of a shape relationship to any axis. Either for a section modulus is to direct measure of the strength of the beam. Z equal to the section modulus formula, that is I by Y. Next, consider a singly reinforced beam shown in figure. This singly reinforced beam we can assume. Okay, it is a simply supported beam. Left end of the beam is simply supported, and right end of this beam is having a roller support. And the load is placed at two areas at L and L, that is from left side and right side L, and the distance between the two loads is called as L by 2. At the cross section XX, which is the following statement is true at the limit state. Option 1 the variation of stresses is linear and that of strain is non-linear. Second one, the variation of stress is linear and that of stress is not linear. Third one, the variation of both stresses and strain are linear. And fourth one, the variation of both stresses and strain is non-linear. Which one is correct? B. How அப்படின்னு பார்த்தீங்கன்னா, for the limit state method at any cross section XX, the strain variation is linear and the stress variation is non-linear. And this is how the stress distribution diagram will be there. The first picture which indicates the cross section of the section, and the second one will be the strain variations. Normally strain variation பார்த்தீங்கன்னா நம்ம moment diagram-ஓட அப்படியே ஆப்போசிட்டாக இருக்கணும். டாப்ல வந்து positive தான், positive alone will be there, but it should be in the left hand side, whereas in the bottom portion it should be in the right hand side. And the stress variations will be in the concrete alone, because at the bottom portion the steel will be taking care of the stresses. So only at the concrete portion the stresses will be there. Okay. Next, from here the 2-mark questions will be started. Okay, இது வரைக்கும் பார்த்தது எல்லாமே it is just a 1-mark question which will be asked in gate, whereas from here only the 2-mark question starts. A 450 mm plain concrete prism is subjected to the concentrated vertical load as shown in figure. The cross section of the prism is given by 150 mm by 150 mm. Considering linear stress distribution across the cross section of the modulus of rupture expressed in megapascal. So for this we have to calculate it. So in this diagram they have mentioned the load and the distances. Okay, the load is acting at L by 2 distance, sorry, L by 3 distance the load is acting, and this section is a symmetrical or asymmetrical section. Symmetrical, yeah, we have good, At the left hand side, you will be having a simply supported beam, whereas in the right side, you have a roller support. But the distance and the loads are same now. We cannot say it is a symmetrical beam. Okay. For this, we have to calculate the modulus of ruptures. The maximum bending moment will be 11.25 into 0.15. 11.25 will be the load and 0.15 will be the distance. Because load is mentioned in kilonewton, so the distance also should be converted in from mm to meters. Okay. So load into this distance. Potamna will be getting the maximum bending moment. Before that, we have to calculate the reactions at A, that is reactions at P and reaction at S, we have to calculate. So what is the formula to calculate the reactions? Load, we have a same loads. So reaction at P will be 11.25 and reaction of S also will be the same 11.25. Since we have the same load, here the support load there is no connection. Only we have to use the load. So we can take it. Next formula to calculate the modulus of rupture அப்படின்னு பார்த்தீங்கன்னா M by Z. M will be the moment of inertia and Z will be the section modulus. Moment கண்டுபிடிக்க என்ன formula?
Sir, load into perpendicular distance.
Good. Load into perpendicular distance. That's what they are here also they have added. So load, that is the 11.25 into perpendicular distance is 0.15 and into 10 power 6 they have converted that kilonewton meter they have converted into Newton mm. Okay. So the breadth and depth, it is 150 into 150 squared. If you substitute, you will be getting 3 Newton per mm squared. Okay. Similarly, next problem. A cantilever beam of length 2 meter with a square section of side length 0.1 meter is loaded vertically at the free end. The vertical displacement at the free end is 5 mm. The beam is made of steel with the Young's modulus of 2 into 10 power 11 Newton per mm squared. The maximum bending stress at the fixed end of the cantilever is. They are given options. So how to calculate this அப்படின்னு பார்த்தீங்கன்னா first thing we have to calculate the displacement, that is the deflection. So since it is a cantilever beam, where will be the maximum deflection? The maximum deflection will be at the free end. Okay. So the formula to calculate in பார்த்தீங்கன்னா del equal to WL cube divided by 3EI. This is the formula to calculate the maximum deflection. Where the maximum deflection is given, that is 5 mm. So if you convert it into meter, it will be 5 into 10 power minus 3. Load alone we have to calculate. So L also it is mentioned in the question, that is 2 meters. So W into 2 cube divided by E, it is also mentioned in the question, that is a modulus of rigidity 2 into 10 power 11 into 0.1 divided by 12. You will be getting the load in kilonewton. Then the bending moment A கண்டுபிடிக்கிறதுக்கான என்ன formula? The load into distance. If you substitute, you will be getting the bending moment. And the maximum stress, what is the formula? Just a minute. பூட்டி இருக்குங்களா? சரி, நாளைக்கு அடுத்த வர கொடுத்துருங்க. And the maximum bending stress, what is the formula? Same, sigma equal to M by Z. So if you substitute in that formula, you will be getting the stress, that is 37.5 Newton per mm squared or megapascal. That's all about the failure theories. Now we are going to see about simple bending theories. Guys, do you have any doubt up to this?
No, sir.
Okay. I think I will be definitely going faster because the entire semester what we have studied, I am taking in just 2 hours. So it will be a little bit faster only. No other go. Kindly come with me. Okay.
Okay, sir.
And if you have any doubt in anywhere, no, you can just stop me and you can ask your doubts. Okay. Okay. Now we are going to see about the simple bending theories. Sorry, simple bending theories. In that two beam, one having square cross section and another having a circular cross sectional area, are subjected to the same amount of bending moment. If the cross sectional area as well as the material of both the beams are same. What they are saying அப்படின்னா the cross sectional area of two beams, one is circular and the second one will be in the square shape. Both the area is same and the material used is also same, in which the maximum bending stress developed in both the beam is same வருமா? Definitely not. The circular beam experience more bending than the square beam அப்படின்னு காட்டிங்கன்னா definitely yes. What is the reason அப்படின்னு பார்த்தீங்கன்னா the cross sectional area with the ratio to volume அப்படின்னு பார்த்தீங்கன்னா circularக்கு it will be more when compared to a square or rectangular sections. அதனால தான் இந்த even a single drop of water கீழே வரப்ப என்ன வரும், it will be in a circular area. The circumferential area will be lesser and the strength will be more. ஓகேங்களா? By using some formulas and other things also we will be proving that. Okay, what are the formulas அப்படின்னு பார்த்தீங்கன்னா for a square section, what will be the maximum bending moment அப்படின்னு பார்த்தீங்கன்னா m by I into y. This is the formula. M will be the moment. I வந்து என்ன formula? Section modulus sorry, moment of inertia வந்து for rectangular BD cube by 12. Since it is a square, we will be taking it as a power 4 divided by 12. Y வந்து instead of d by 2, we will be taking as a by 2. Substitute பண்ணோம்னா 6m divided by a cube ன்னு வருது. In case for a circular section, m by I into y. So I பார்த்தீங்கன்னா என்ன formula for a circular section? Moment of inertia formula is pi d squared by 64 and for y it is d by 2. If you substitute it, you will be getting 32m divided by pi d cube. So the area of the square section is equal to area of the circular section. So A is equal to AC போட்டோம்னா A squared, that is the area of square section in a formula A squared and the area of circle formula pi d squared by 4. This solve பண்ணோம்னா you'll be getting the 0.886 D. அதே மாதிரி for stress, if you substitute both the stresses of a circular and rectangular section substitute பண்ணோம்னா you will be getting sigma 1 equal to 0.847 sigma 2. அதாவது sigma 1 வந்து sigma 2 ஓட கம்மியாக தான், 1க்கும் கீழே போகுது. ஸோ 1 வந்து என்னது, it is a circular square section. அதனால second one is correct. Next, a cantilever beam having a square section of 10 mm by 10 mm, it carries a transverse load of 10 Newton. Considering only the bottom fiber of a beam, the correct representation of longitudinal variation of bending stress is. Here, in the diagram, they have mentioned the cantilever beam and a load of 10 Newton is acting at the center portion of the beam. And the cross section of the cantilever beam 10 mm by 10 mm. So what will be the longitudinal variation in bending stress? அப்படின்னா we have a formula. The same bending stress formula m by z or mi into y. Anything you can consider. Okay. In case of Z அப்படின்னா BD squared by 6. M will be 0 between B and C. We will be assuming the B point at the end of the beam and C as the midspan. So at that particular point, we don't have any load. So moment will be 0. And hence the bending stress is 0 between B and C. The bending moment at A, that is MA equal to 10 into 1, that is load into distance. And the bending stress at A is equal to sigma A equal to 10 into 10 cube divided by Z value. If you substitute, you will be getting the bending stress. Bending stress at 60 Newton per mm squared. Since the bending stress for cantilever beam, it will be in a linear position. அதனால linear we have drawn it. In case if it is a UDL இருந்ததுன்னா, we have to go in a parabolic shape. In this sum, it is a pointer, so we will be mentioning in a linear diagram. Okay. And what is the maximum value of bending moment? For the maximum value of a bending moment, here it is 13.5 kilonewton per meter. How it is taken அப்படின்னா, the size of the section they have mentioned here, that is the span of the beam is 6 meters and the load acting on the beam is 15 kilonewton per meter, and cross sectional area will size of the beam is 75 mm diameter. If you substitute in the maximum bending moment formula, what's the maximum bending moment for a UDL simple supported beam அப்படின்னு பார்த்தீங்கன்னா WL squared by 8. This is a formula to calculate it. Here W is known, that is 15 kilonewton per meter, and L will be 6 meter. If you substitute in this formula, you will be getting the 13.5 kilonewton meter. That is the maximum bending moment.
Sir, how 3 came, sir?
For a UDL, what is the formula அப்படின்னு பார்த்தீங்கன்னா load into distance by 2. That is the formula, right? So loadங்கிறது வந்து it is 15 kilonewton per meter. Just a minute. Okay. Guys, the normal formula for UDL அப்படின்னு பார்த்தீங்கன்னா bending மட்டுக்கு என்ன formula? Load into distance by 2. So load is 1 kilonewton and the distance is 6 meters. So distance by 2, that is 3. Okay, that's how you have taken. At the starting itself, I have mentioned, no, I think you have forgotten. Okay, next, what is the maximum value of bending stress? பார்த்தீங்கன்னா the bending stress for a rectangular section, they have mentioned the section, but that particular section is diagram is missing. Yeah, tell me, Pa.
Sir, can you move to the previous problem?
Yeah.
Here W is 3.
So W is equal to load, no sir. Load means here directly
Yeah, the
given
load is 1.0, I think so.
1.5 or 1.
1.0 it is. I think
But in the
it's
formula
not
itself,
that much clear.
If the load is 1 means W will be 18, sir.
Just a minute.
No, sir. For this time, directly
Yeah,
we can take load,
there is
sir.
there is a small mistake in this problem.
W is equal to 3, sir. Yes, sir. Only
Yeah,
W is equal to 3 or
yeah,
W is
W
equal
is
to
3.
50.
Yeah, there is a small
Yes, sir. Yes, sir.
yeah. There is some misunderstanding in
Correct, sir.
this
W is equal to
value.
3.
Yeah,
Yes, sir. W is equal
we
to
either
3.
we have to change it. Instead of 1.0 or 15, it should be mentioned as 3.
Yes, sir. Yes, sir.
And in the next problem, what is the maximum value of bending stress? Here also the diagram is missing in this problem. So we'll go to the next one. Okay. Okay, guys, a small thing. You just to go through this problem in 2 minutes. I'll come and join. Okay.
Okay, sir. Okay, sir.
மேப்பிங் அனுப்பிச்சிருக்கிறேன் மெயில் மட்டும் வெரிஃபை பண்ணிடுறேன் அந்த கிளாஸ் அடுத்த நாளைக்கு
Okay, sir. Thank you. Okay, guys. For the interruptions, have you seen about this problem? Do you have any doubt in it, or you want me to explain this problem? Guys, have you go through this problem? Guys, am I audible to you? Guys, am I audible to you?
Sir, yes, sir. Your voice is clear, sir.
Oh, okay. Because I don't able to hear any one of your voices. That's why I'm asking you again.
Guys, anyone can interact with sir, ma.
Okay, guys. Okay, guys. Have you seen this problem? Do you want me to explain it again?
Sir, some noise is available, sir.
Yeah, because the college has been over by 3:30
Oh,
sudden. That's why
okay, sir.
there
Okay,
are
okay.
few noises.
Okay, sir. Okay, okay. No issue, sir. No issue. Okay, sir.
Guys, do you want me to explain this problem?
ஏய் கண்ணா ஏதாவது டவுட் இருந்ததுன்னா கேளுங்க கண்ணா நோட் பண்ணுங்க சார் நீங்க ஒரு 3:45 வரைக்கும் வேணா எடுத்துருங்க சார் நோ இஷ்யூ
Okay, sir. Okay, sir.
ஓகே சார்
Okay, sir. I will explain this problem. Mass-less beam has loading pattern as shown in this figure. The cross section with the width of 30 mm and the height of 10 per 100 mm. This diagram they have given that this simple supported beam, and the left portion you will be having the simple supported beam, and at the right portion you will be having a roller support, and you have a UDL load also. That is 3000 Newton per meter. For meter length only they have given, and the dimension is 2000 and 2000 they have mentioned. For this we have to calculate the maximum bending moment at. So where the maximum bending moment will be, பார்த்தீங்கன்னா either it will be in at the located at B, or 2675 mm at right of A, or 2500 mm at right of A, and 3225 mm at right of A. At which portion the maximum okay. If this 2675 mm or this 2500 mm is not mentioned அப்படின்னா, we can directly mention it as it will be locating at a midspan between B and C. Directly we can mention, but it is not located like that. So that we have to find solve the problem. Okay. So the maximum bending moment at A will be 0, since it is a simply supported beam, and the bending moment at shear force is as 4.5 kilonewton, and VA plus VC equal to 3 into 2, that is 6, and VA will be 1.5 kilonewton. And here let us consider the section XS, which is at a distance of X from C, and the shear force equal to 4.5 minus 3x will be 4.5 minus 3x, that will be the shear force at X. The maximum S of 1 பார்த்தீங்கன்னா will be 0. And the maximum bending moment பார்த்தீங்கன்னா 4.5 minus 3x is also equal to 0. So x is equal to 4.5 by 3 equal to 0.5 meters from C. So the maximum bending moment will be occurring at a distance of 4,000 meters at 2,500. Option is, and the next question is the maximum magnitude of bending stress in megapascal is given by. Here also the diagram is missing, so we will go with the next problem. A single supported beam of length 3L is subjected to a load shown in figure And this is also the same. This is simply supported beam. At the left portion, the beam is simply supported, and at the right side, it is having a roller support. And the load is located as by 3 distance. Okay, it is given that P is equal to 1 Newton, L is equal to 1 meter, and Young's modulus is equal to 200 Pascal. So the cross section is square with the dimension 10 mm by 10 mm, and the bending stress at a point A located at top surface of the beam at a distance of 1.5 L from left end of this. For that we have to calculate. So how to calculate this is the diagram and the method is to solve. First at the moment at beam it will be 0, and moment also will be 0. Since it is supported and a roller supported beam, the bending moment will be always equal to 0. And it is in the upward direction and y in the downward direction. How it is possible? The diagram they have mentioned. நிறைய பேர் இந்த arrows will be missing. Because load it will be always moving in the downward direction. Whereas here they have mentioned the pull as and the load. Okay. So for that we have to calculate individually, and finally the bending stress should be calculated by using the formula M by Z. Okay guys, I think there is a lot of surrounding noises. We will wind up the class, and I'll share my PPTs to Parthasarathi sir. Okay, you can get it from him. Okay, okay guys, do you have any doubt up to this? Guys, do you have any doubt?
Yes, sir.
Sir,
Hello, Naveen sir. Nice.
yes,
Okay.
Parthasarathi sir.
So notes எடுத்து வச்சுக்கோங்க. So we will discuss in upcoming classes. Okay. Thanks to all. You can leave this class. Naveen sir. Thank you, sir.
Thank you so much, sir.
Thank you, sir.
Thank you, sir.
Naveen, sir.
சார் சொல்லுங்க சார்.
அங்கேயே ஒரிஜினலி இல்லை அப்படின்னு சொன்னாங்க மேம். அதான் இப்போ ருப்பி அமௌண்ட் மட்டும்
எவ்வளோ
கொடுத்துருக்காங்க.
டேய் கண்ணா, கிளாஸ் முடிஞ்சிச்சு, கிளம்பலாம். This call recorded will be everyone apps.